Well, we've covered a lot of territory today, and I want to spend just the last few minutes that we have together try to maybe take a step back and refocus. I mentioned this morning, use the laureates to tell us, just give us a little perspective on why is this important, what should we be thinking about moving forward, and as we go back into our daily lives and working on a daily basis, remembering what's important. So today we have, to give our final laureate perspective, we have Dr. Mark Sobsey, who is the 2016 Clarke Prize laureate. He is the Keenan Distinguished Professor of Environmental Sciences and Engineering at the University of North Carolina at Chapel Hill. Mark Sobsey.
Thank you very much. Can all of you hear me okay with this microphone? Okay. So I'm a last-minute substitute for George Trebanaglis, or George T., as he's fondly known. And actually nobody can substitute for George T. So I say that because I actually would have preferred to hear what he had to say. Nevertheless, as a last-minute substitute, I cobbled together a few slides that I think they're queuing up soon to give you a little bit of a notion of where I think we're headed in some areas of hot topics, some of which you've already heard about already, that are unmet needs, primarily in the area of microbiological aspects of water quality and health. And I bring these to you as examples of things that I'm working on because I think that these are the sort of hot topics where young people, especially since there are a lot of younger folks in the audience here, students, postdocs, junior employees, where there are real opportunities. And I say that because I think the future lies in your ability to be creative, be innovative, take chances and risks. And if your gut tells you that this may be worthwhile to explore, try and figure out how to do it, because I think that's what we need from all of you who are the future, the future leaders in our field. So I'm not sure where the button is to advance these slides. I guess this is it. So some of this is from my Clarke Prize presentation of last year, and so I'll be posing some questions that I posed previously. So despite the sanitary engineering and microbiological revolutions and advances that occurred more than 100 years ago, we need to still ask, why do so many people still not have access to safe water and proper sanitation on a global basis? So there's still a huge unmet need, which other speakers have already indicated. And I think it means that we tend to get caught up in our own little world, such as here in Southern California, and a preoccupation with highly advanced technologies for reducing logs of microorganisms in double-digit figures. And yet we know that there are people who struggle to just find any kind of safe water or have proper sanitation. So my answer to the question I posed is that we actually have to think about achieving the UN Sustainable Development Goals of 2015. And if you don't know what they are, I have a slide coming that shows you briefly what they are, many of which are related to water sanitation and hygiene and public health. So I think it means that if we're going to have safe water and sanitation, we actually may need to set some new goals, create some new frameworks and implement them, take some new approaches and make some new plans, and take a broader health risk-based focus, use new assessment and analytical tools, and engage a broader range of stakeholders. We tend to stay highly compartmentalized, and we need to start talking across our silos and engage with one another, and especially the public. So those are things that all of us, I think, are going to have to do. These are the 2015 Sustainable Development Goals. Goal 6 on the upper right is the one that is intended to achieve global access to safe water and sanitation by 2030. This is a huge commitment, and one for which there's a new flurry of activity. but it's also supported by related goals that have to do with maternal and child health, environmental protection, sustainable agriculture, and lots of things that are interconnected to our interest in water sanitation and hygiene. So for goal 6 for water, the new initiative says that we should measure the microbial quality of water wherever people drink it. Because right now, water in developing countries is mostly not tested. Here we test water all the time, right? And wastewater as well. But where testing sometimes is done, it's done for the wrong reasons, and sometimes no one knows actually what happens to the data. Someone comes and collects a sample, takes it off to some laboratory that who knows how far away it is, and they do a test, and maybe the numbers get filed and they go into some database that the community never sees. So what we also know is that a lot of testing can't be done in low resource settings because there are no labs. It's too far away to get samples back to a lab. And so we don't have easy, simple, self-contained, field portable tests to bring water quality testing into the field where the water is, maybe to be done by local people. And so, so I decided that with the help of my students, we should develop such a test. It's called the compartment bag test, and it goes back to first principles, where you collect a sample of water, such as in the upper right, and you add a bacteriological medium to it and let it dissolve. And then you dump it not into a series of test tubes for which you need pipettes and test tube racks and all that stuff. Put it in a plastic bag that's got 5 internal compartments that add up to 100 ml, each one a different size, so that you can get an MPN estimate after the bacteria grow, which they can do at temperatures between 20 and roughly 45 degrees. So you don't need an incubator. You can incubate at ambient temperatures. Wait for the bacteria to grow. We're looking for E. coli. If E. coli grows, the water in the compartment will turn blue. That's a positive result. Then there's an MPN table that comes with the test, and you just look up which compartments are positive and negative, read the results. And so people wanted this as soon as they heard we developed it, and so a company was spun out of the university, and this is now a company in its 5th year of operation, and this test is sold all over the world. And people love it because there isn't anything else like it. My point is, think simple. Bring things that could be created that don't exist. And you're the ones who should be able to do that. Because if an old man like me can do it, there's no reason why you shouldn't be able to and do it better. So this is just an example. Another thing that we have is a situation where many people don't have pipe water supplies. So they have to go fetch water and then figure out what to do with it to try and make it safe. So until about a couple of decades ago, this whole concept of point-of-use household water treatment in the developing world didn't really formally exist. And so it has now become institutionalized that indeed people can treat water potentially very effectively by simple methods. As you might expect, they can boil it, they can chlorinate it, they can put it in the sunlight to disinfect it, they can run it through some kind of porous ceramic filter, which could be locally made, or they can pour it through an intermittent flow slow sand filter, which they can also locally made. So there are tremendous unmet needs in this area as well. How can we make these technologies more accessible? How can we improve them? For example, the microporous filters, they don't take out viruses. So what can we do to make those kinds of filters better at capturing and removing viruses? There are many ways that we could think to do that. Think about it and see if you can figure out how it could be done. So what about waterborne enteric viruses? Everybody's really interested in viruses these days because we know that a lot of waterborne disease is caused by viruses, hepatitis A and E viruses that cause infectious hepatitis, norovirus, which is the biggest viral cause of gastroenteritis globally and is waterborne as well as foodborne. And yet we still struggle to know how to best detect these viruses. And you've heard Joan Rose already today mention that indeed we're still trying to figure out what the best way is to detect these viruses. We have these new molecular methods, but they don't tell you if the viruses are infectious or not. We have the older cell culture methods where you inoculate a monolayer of mammalian cells, and then you wait for the virus to infect the cells and kill them. So going from the upper left on the panel on the right, where you have a nice healthy cell layer, over a period of time, the cells die, and on the lower right, you see what that looks like after a while. Many viruses actually grow in cell cultures and don't do this. So how are you going to detect them? They're in there and they're growing. We could use molecular techniques for that, and we do, but we still haven't optimized the methods for this. So there's plenty of opportunity for those of you who are here to try and advance these molecular methods and make them faster, make them better. And I would encourage you to think about this if you're interested in microbiology. Lots of opportunities there. We also know that we actually do need indicator viruses probably. And after several decades of trying to convince EPA and others that we should be working on viruses along with with bacteria as well as protozoan parasites, EPA's finally gotten the message, and there's an initiative underway to bring fecal indicator viruses, probably these coliphages, these bacterial viruses that infect E. coli, forward as criteria for wastewater treatment plant performance as well as recreational water quality. Because we already have a rule that says that coliphages should be controlled, at least in groundwater supplies. And we could probably take better advantage of what they tell us about the virologic quality of water. So we know that there are diverse numbers of them. We still don't know, well, which are the important ones? What's the best ways to measure them? How can we actually get down to measuring them quickly and easily? So lots of opportunities for improving our ability to identify the most appropriate ones, the most effective ones, the most predictive ones of human health risk, and getting methods to the point where you can try and measure them quickly and get results for quick answers. Same-day results, for example, to decide whether or not you should open or close a beach. Now, Chuck Harse, our laureate for this year, and Joan Rose already mentioned antimicrobial resistant bacteria. This is an important topic because we know that we have a problem with the fact that we've run out of new antimicrobials. There haven't been new ones for quite some time. We know that there are different kinds of antimicrobial mechanisms of resistance, and that whatever clever ways the world of chemistry has figured out to try and kill these bacteria, prevent them from growing, they have clever ways of overcoming that. So we're now at the point where we don't have new antibiotics in the pipeline, and bacteria are becoming profoundly resistant even to the 4th and 5th generations of antimicrobials of last resort. So this is a problem. It's a medical problem, it's an animal health problem, but it's an environmental problem. Why? Because these bacteria are everywhere. Now, some are already in the environment from the get-go, but we have hotspot sources that we need to worry about. And I skipped a slide here. So what we have to take is this One Health approach to recognize that we have to link up the occurrence and importance of antimicrobials in humans, in animal agriculture, and in produce agriculture, because we irrigate with wastewater, especially globally, and that these bacteria in the environment have to be controlled, especially from hotspot sources like sewage. And for example, hospital sewage as another important hotspot, and animal agricultural waste, manure, because we still promote growth of those animals with antibiotics. So this is important, and we need to really pay more attention to it. And we actually have to develop better methods to look for these kinds of bacteria and monitor their presence in these hotspot sources and more generally in the environment. So we currently do not have a global system for this, although I should qualify that because one has just been initiated. And what we want to do is develop a robust culture-based method to detect target indicator antimicrobially resistant bacteria in the environment. And this is a system that should be accessible to any country in the world. So that means it's got to be dirt simple. This is basically spreading spreading samples on culture plates of antimicrobial resistant media and growing the bacteria, counting the colonies, and comparing the number of resistant ones for certain antimicrobials to the total population of those same bacteria, say E. coli. We already measure E. coli. We know how to do that. We can measure for extended spectrum beta-lactamase resistant E. coli or carbapenem resistant E. coli. And it turns out that it's easy to do because you just put the antibiotics in the medium and then you can grow them and compare the number on those plates to the numbers of total E. coli on another plate. So this is what we did. We did it in hospital sewage, and we did it for ESBL E. coli as well as coliforms and the carbapenem resistant ones. And a fair proportion, a scarily fair proportion of the E. coli and coliforms in hospital sewage are resistant. Those are the red or blue bars on the circles on the right. So that's in hospital raw sewage. This is community raw sewage, and there's still a fairly substantial slice of the pie that's in the community raw sewage, including the carbapenem resistant ones, so they're a few percent. They're there. And then in the secondary effluent, about the same. They're still there. They don't go away. Some people said, oh, well, they're going to disappear because of the pressures of wastewater treatment. Ain't happening. So these bacteria are getting into the environment. If this gets discharged into the environment, that means these bacteria coming back into the environment. And if you're swimming downstream or something like that, you could be exposed. So this is an area where there are tremendous opportunities and there are tremendous needs. And the World Health Organization has just initiated a global plan to measure focusing on ESBL-resistant E. coli. And I've been fortunate enough to have contributed to that effort based on the work that we started to do 3 years ago to show that this was possible. But this is easy peasy microbiology. This is culturing bacteria on plates. You have to be strategic about what you want to culture and for what motivations, what reasons. And I encourage you to approach your own research that way. So the future is that we need to do a lot more things. And there's still too many people who still lack access. Pipe water and wastewater systems are way too deficient in many ways around the world. We know that point of use household water treatment can be improved, it can be made more sustainable, and people can maybe be better encouraged to take it up. And we also know that there are important goals that have to be achieved to take the science that we produce and get it into policy and practice. I think if we're going to be making real contributions, you have to get stuff out of the laboratory and into the hands of people who can use it. And we're going to have to engage with other stakeholders to make those sorts of things happen and to work collectively towards achieving the sustainable development goals in the water and sanitation area and figure out how we can best take what we do and bring it forward so that it has an impact in the real world. At least that's my perspective. So I'll leave you with that, and I know that some of you need to get on the road before the traffic builds up too bad, or it may have been too late already, but thanks for your attention.